test 1, 2, 3. Okay. I want to show an example that links feature augmentation and kernel together. Last time we talked about the basic idea of kernel function. You have original feature x. You can lift it to a higher dimensional space where you can use it to formulate our more complicated function families for regression. And then you can compute the kernel function as the inner products of the lifted feature h of x. So the kernel idea stems from the dual solution to kernel ridge regression. This path illustrated on this diagram as this yellow path. You go from original feature x, map to h of x, and then come back to one scalar function, kernel function, the similarity between two features. This is so-called explicit lifting. One way of calculating the kernel function through explicit feature lifting. But kernel regression, we are more into the shortcut illustrated here, the straight line, bottom path, implicit lifting. In order to calculate the value of kernel function, you don't have to explicitly calculate h of x. It's just a nonlinear function of original features, x. It's a pairwise function. It takes x and z, it spits out a number. Consider this, only 10 points. I have 10 points in black dots. I generated these 10 points, assuming this underlying model in light gray. It's a slanted curve superimposed with sinusoidal wave, okay? I have this underlying model, I don't know. I sample points from this space according to this function, add some noise to y, okay? Given these 10 points, if I go for polynomial feature regression of order 1, basically I want to fit a line through these 10 points. This dotted line is the best line I get for this 10 points. The red one is this, when I go to the polynomial features of order 1, I have two functions. One is a vector of all ones. That's the red line. The second one is a linear function, x, okay? And that's a green line. But I have scaled them by the appropriate weights I found in this linear solution. Okay? Essentially, it's a linear regression over the augmented feature. In this case, it's polynomial feature of order 1. Basically, the dotted line, the final solution, is just weighted combination of the red line and the green line. If I add the red line and the green line together, that gives me the dotted line. Yes? I actually know the form of the red line and the green line to begin with. The least square regression on these features is just to figure out what is my W1, what is my W0. I just need to figure out the weights. So the red line will go up and down. The green line will tilt around origin. Okay? if I go to polynomial order 2, I have one more basis, and that is x squared, and that's the blue line I get. Now my fitted solution has a little bit of curve in it, right? Again, it's this dotted black line. That's my best solution, okay? And that dotted line is just the sum of the red line, the green line, and the blue line, okay? If I go to polynomial order 3, I have one more basis. That's x3, okay? And this takes this cubic curve shape, and it's in cyan, okay? And again, the dotted black line, the best polynomial regression curve is the summation of this red line, order 0, green line, order 1, the blue line, order 2, cyan line, order 3. All of these added together, okay? Last time, when we talk about feature augmentation, there's another family we have not explored much. That is a radial basis function, okay? Let's consider radial basis features, okay? And I have chosen the location of each bump. Each RBF is a Gaussian bump, okay? These are my basis function. Instead of either the horizontal line, slanted line, cubic curves, I have individual bumps. In this case, I assume the location of the bumps are chosen at fixed point here, okay? Each of these marked location, there's going to be bump. So now instead of these bases, I have these bumps, and I need to find the weights over these bump basis functions. And you can see this. Again, I'm color coding these bumps, and I have scaled the bump according to the weights I have found. Okay. For example, at this location, you can see the peak value is 2. So, and the Gaussian bump essentially is defined by x minus this x bump, center, say mean. So you can think of at the peak, at this mean location, this value is going to be 1. So now this value is 2. So I know the weight for this bump is 2. Yes? So you can see some bumps are bigger, some bumps are flipped back, inverted, because here you can see if I read out is almost -5, right? So that's the weight for this bump. When I add all these bumps together, this will give me this dotted black curve. I mean, it feels like, it goes through color because they overlap. In this case, the sigma is only 0.5. It's very small. So each bump only covers this area between the sampled points. So, for example, this bump, roughly in this region, it quickly dissipates to 0. Beyond that, it's not seeing much. This basis function is not contributing to prediction beyond this limited zone. As a consequence, even without looking, at where my sample black points are, I know that, essentially the weights I could have, is only trying to fit the individual points. And this will be more clear when we go to, if we drop the centers right at where samples are. But you can see that the dotted line essentially follows the individual bumps. It's a useless regression. right? It will predict, for example, if I have a test point here, the prediction will be this point. If it's here, it will be this. I actually don't need to see the points beyond this region. I don't need to see this. I can just figure out who is my closest sample point and what is this bump, and I can just read off the value from this individual bump. It's not trying to link all these isolated bumps together, because the field of view is very small for individual bumps. Okay? If I increase the spread of each bump, now sigma is 1.0, you can see that now, these bumps takes particular shape, and the composite, which is the dotted black line, has a more interesting shape, right? For example, this region, it's essentially this red bump and this dark red bump added together create this interpolated value. If I have a test value here, it will give me this reading instead. If sigma keeps increasing to 1.5, then you can see each bump has a larger governing area. So the fitted value, if I have a bump like this red bump, in order to fit this value, what are the relevant bases? There's a blue, the blue is almost 0. The red has some value, the yellow has some value, and the green has some value. So it has to be the linear combination of these active bumps must sum up to be this black dot. Okay? But all in all, if you look at the black dotted line, it's not really capturing this linear trend going from left to right. It has a sloping up trend, how the y value changes with x value. So this is RBF basis over fixed locations. I don't need to know where the samples are. I have choose some fixed locations. We talk about a special case of RBF where each basis is just located at each training instance. This is what we have. At a 0.6 sigma equals 0.5, each bump is of the same width, and this is you can see that each bump at the center, I have drawn the line connecting it to its peak. These are where the samples are. Each sample contains a bump. Now I will find the best linear combinations of these bumps in order to fit these 10 points. And then you can see how this dotted line try to follow this light gray underlying model, but the spread is so small, so it has a lot of wiggles. For example, this area, even though this, of course, the samples are very sparse, so it doesn't have enough data to suggest that between this point and this point, because of the small spread of these bumps, it will create this artificial dip. Okay. At the sigma equals 1, like what we have seen from the fixed location RBF features, the results have improved quite a bit. Especially, you can see in this region, the dotted line follows the light gray underlying model fairly well. And if you try to focus on the dotted line, you can see that in the negative zone here and in the positive zone, even though individually is a individual basis function is a bump, piecing together all of them, you can still grasp this. Gradually it's sloping up. And this is when sigma is too large, 1.5. And previous plots, I have scaled the bump according to the actual weights. Here, if I do it by the actual weights, it's going to go over this plot. But in order to give a sense, I just scale all the components by about half so that everything fits. You can see that when the spread is large, each point has a huge influence zone over the entire fitting. And and in a way, if you think about it, the underlying function is much smoother. It's a large, low frequency blob. And but the values, the way it's learned in individual ones, the range is a magnitude higher. It has very large weight on these bumps, and it compensated by bumps of the opposite direction. As a consequence, it fits this, the fitted value is trying to, if you compare to the previous one. This point, they fit, the fitted value is similar, but it results from huge compensation from both sides, positive camp and negative camp. It's the difference that, gives out this value. Okay. Now let's think about the kernel, right? So far we just see the least square regression over features. We play with features. What if I use RBF kernel? Implicit lifting, okay? In the kernel approach, I only know the pairwise similarity between instances. And what I learned is this dual variable beta, which assigns to each point a weight, right? So it's the the grand matrix evolves into this kernel matrix, and I try to find a linear combination beta over k so that equals y. Okay. So the solution essentially assigns a weight to each point, and here I illustrate the weight using the size of these circles located at each point. Positive weights, I give it a green circle. Negative weights, I give it a red circle. The size of the circle is proportional to the size of the weight. Okay? And now I can evaluate, given any point, test point here, using my RBF kernel, I can calculate the similarity of x with respect to xi. And then I can use the beta I to do weighted sum. And this will give me the predicted value at location x, right? This is my prediction. And this is how I plotted my dotted curve. Pure, just numerical. I do not use any approximation, okay? I just sample along these, within the range. For every x, I use this formula. I know the format of this, which is x minus xi. Okay? Every point I can evaluate. Now I have this beta I, which is all these green, red circles. I add them up and I have a value. And this is how I link all these evaluated points together. That gives me the black dotted line. And if you compare, this is over basis features, okay? I hope the transition is smooth enough. So if you just focus on the black dotted line, this is using least square regression over RBF as features. I augment the feature. This is least fit over RBF as a kernel. is the black dotted curve, the solution, are they identical? Does the black curve move at all? It doesn't move. So that means least square regression over RBF basis located at the training instances produces exactly the same solution as kernel regression using RBF kernel. Okay, so this is the case when I increase sigma equals 1.5. This is the solution, and you can actually see, the size of the bump. You see the larger bump if you compare. So this blue is pretty big. This one is also big, and this goes down. So I'm expecting that the weight on this is going negative. This is positive, very large number. If you compare this, you do see very large green circle here and very large red circle here. Identical solution. Here is the math, okay? When I use radial basis function h centered at the training instances, this is not the only way to do the radial basis features, okay? As I have shown previously, you can put a so-called landmarks. You pick landmarks because otherwise, if you have 1 million instances, you have 1 million basis functions. That sometimes is too much. But if they are located at the training instances, so each feature you can look at x1. At x1's bump, essentially the feature becomes this function. Just every other instances evaluated with respect to this center location at x1. And x2 and x3 all the way to xn. I have these basis functions, okay? Compared to if I use polynomial, that would be 1, 1, 1, 1, and x1, x2, xn, and x1p, x2p, all the way xnp. They're really equivalent, right? It's the same format, it's just the basis function is different. And the least square primal objective is to, for this feature, nonlinear feature, find the linear combination of them, linear combination, is to try to approach the target values as close as possible. And once we figure out the optimal feature value, we use this to predict the target value. RBF feature could also be centered in fixed location. Usually people call it the landmarks. Okay? So compared to radial basis kernels, okay, K, in a way, I should not color them, okay? It doesn't have the sense of this column. It just have this K, Xi, Xj, okay? But if you look at the math, right, the term of this is identical to the polynomial features. So K is exactly the H when the RBF features are used. And from this perspective, we gain an interpretation of the kernel function as a special kind of basis function. So I keep the coloring to indicate that. You can think of kernel as a pairwise function that spits out a scalar value. You can also think of by column, each is a specific kind of kernel function defined as K, Xi. Okay? Xi is fixed at this instance, and this is just function. This becomes a function. If I call it a function, this is a particular function X. Okay? So the LS dual objective is to say kernel matrix multiplied by the dual variable should approach Y. And since K equals H, this format is exactly as this format. It's just in this case I call it beta, this case I call it W. So the dual variable solution is identical to this primal solution, least square solution over polynomial features, over the RBF features. And the prediction is this, which is also, since K equals H, they are also identical. So the theory checked out, just like what we observed from the experiments. So RBF feature centered at the training instance is equivalent to RBF kernel. And kernel can also be viewed as a specific kind of feature functions. So that probably, with this view, I hope you can see the connection between different approaches, and especially, even though kernel is an implicit lifting, it has this very nice intuition if you think about least-square regression over nonlinear features. That is, when I see this, how do I interpret this beta value? There is an intuitive solution. In the RBF case, it's simply, there is this betas I solved from kernel regression. It corresponds to, I have the kernel function which decides what this kernel basis function should be. It's a bump, okay? And the final solution is just all these, weighted bumps superimposed together. Does this example help understanding kernel? Any questions? Yes. Say that again? Kernel, so the question was, you don't understand why kernel is a dual of least square. So for kernel ridge regression, we have a primal solution, yes? That's clear, okay? The dual solution is based on the solution W has to belong to the range of X. So I can express it as X times beta, okay? So this part is through this ridge criterion, through the fundamental theorem in linear algebra, the null space component has to be 0, so it can be expressed as a linear combination of X. And then we introduce a dual variable, beta. And then we plug into this criterion. Since W is gone, it's only a function of beta, and it results to this, this solution instead. But if you look at this, the prediction can also be re-expressed as a linear combination of beta I and this inner products between the lifted feature, explicitly lifted feature. H transpose is essentially calculating HXI and HXJ on the training instances. So all you need is just the kernel function. So this is where, since I only need this, why don't I just need a function, a black box function, given xi, xj, or xi and x, any test point x. So long as I can return this function to you, I don't have to calculate h. So this is a ridge solution in the primal space. The W is d times 1. And this is n by n times 1 is the dual space representation. This is what I'm trying to illustrate here. You have two views, they're dual to each other. Because W can be equally represented as a linear combination, the connecting equation is x times beta. The primal variable and the dual variable are connected through x. Okay, I mean in this case, in the lifted feature space is actually h, the lifted feature. Okay, Okay. Any other questions? Yes.
So polynomials are universal approximators, right?
Yes.
And also, within the basic function is equivalent to infinity lifting, right?
Infinity lifting.
Lifting to
yes, Gaussian kernel. Yes,
right.
That's right.
And in this case, doesn't it just remember like every accent, like?
If the sigma is too small, right? In the sigma is too small, that's kind of you can see in this example. Even in the kernel case, because the kernel or feature view is identical. Where's my RBF kernel? Yeah. So this is actually, you see, this, I don't need to solve the problem. If the sigma is too small, each bump is just a lone man's island. And this value, I know it got to be xi, yi. I'm not fitting anything at all, right? So it's just memorizing the data. It doesn't have any generalization much. And then within this, it's just nearby bumps adding together. If sigma goes to 0.1, now it is really becoming just like this, each bump like this. Everything, just so long as they're slightly away from the sample points, I know the predicted value will be a trivial 0. That's called really memorizing. It's overfitting to the extreme. If it's xi, my training instance, it gives me yi, very precise. Any deviation from the training instance, it gives me 0. Okay? Okay. So, now we're going to continue to talk about total least squares. Okay? We talk about total least squares as the case from probabilistic point of view. It's the first time in this class we introduce noise in the variable x. All the variation you have seen always assume noiseless x. The domain, the x is untouchable, is given. We treat it as, ground truth. There's no noise. But what if there is, this is actually measured data, there is noise in it. So in the ordinary least square regression, it's noiseless data, and you try to fit it. You try to fit linear combination of x approaching y. In TLS, you have noise in both x and y. Okay? So you assume that, if you remove the noise somehow, they have underlying model is a linear relationship. That's why we write the model as such. You can see that because you have two variables, in the MAP view of this model, you have the product of these two. It's very difficult to come up with a linear solution. And for TLS, we start to look at the regression from a very different perspective, so-called low rank approximation. So this is another way of looking at regression. What is linear regression? Given data x and y, we want to approximate y as a linear function of x. Okay, linear combination of x gives you y. Of course, the actual data has noise. you can have, probably you cannot achieve that. It doesn't fit as well, so it's just approximate, okay? In the OLS, because X is noiseless, I can only say, I'm gonna wiggle my Y so that they form, on these points. This is the best line I could have, so I'm gonna, each Y, I'm gonna, add this perturbation amount, so every point now becomes line up on this line. This is what this means, okay? Because X, I cannot do anything about it. There's no noise. But any line, if I allow to take any adjustment, it give me a crazy line, right? That's not what I want. It can approach any line. I need a line that, I only add minimum adjustment to it. So I think I'm not disturbing the system. If the underlying model is a linear model and I have some observation noise, I try to say minimum adjustment, I can discover this line. If I add too much to it and I have a linear solution, I'm injecting too much into it. I'm making up a model, okay? So this is what OLS perspective. I'm gonna minimize the adjustment in the Y locations so that after adjustment, it falls exactly on line. TLS, because there's a noise in X as well, I'm allowed to adjust both X and Y. After I made the adjustment, you can think of in a point, initially these are my points. I can move any way I want, move away from this. Somehow they line up. Everything's zapped onto this line. Okay? Again, I don't want to inject too much. I think the best solution is the one that requires minimum adjustment, yet it gives me this linear relationship, because I believe the underlying model is a linear model. Okay? Since we have been on the path of probabilistic view of regression, there's a sort of this connection, because to find the most likely value of Gaussian is just a bump, most likely is located at peak. The closer I am to the mean, the more likely that value should be. Here, I'm just minimizing the distance to the mean. And the mean, because this is error, the mean of this noise, the noise is 0. So TLS seeks a linear approximation. After I made the adjustment, they are linear relationship. Okay? And if you look at this joint, if I look at the joint representation between X and Y, it must have rank less than D, because this thing can be written as X plus EX, and the Y is just a linear combination of if here you have a bunch of columns, and this Y is just these columns, a linear combination of this. So this is not going to add anything new to whatever the rank it has, right? That's a fundamental theory of linear algebra, yes? And this matrix is n by d. I add Y, which is n by 1. Even though this whole thing is n times d plus 1, this rank will not be more than d. Yes? Because I'm seeking this reduction. When they line up, one can be represented by the other, right? I'm removing some degree of freedom. If you look at the constraint function, we can say something more about it. Not just the rank is one rank less, one value less. We can also say more about the form of this solution. Since the constraint, we have to satisfy this constraint. Here in this equation, initially we only have W. All we have studied so far, we have only one variable W, which is d by 1. Now we introduce the error, prediction error. It's just rewriting the equation. It doesn't change anything. I'm introducing EX, EY, which is m by 1, twice of that, right? Sorry, this is EX is n times D, EY is n times 1. I have more variables now. Instead of W, it's just D by 1. So what happened? They cannot be arbitrary. This is the constraints they have to satisfy. Only among those that, when this condition holds, any EX, EY, such that they become perfectly lined up, after adjustment, it becomes a line. Among those, I want to seek the one with the minimum norm, minimum adjustment. So this equation in the matrix form shows that W minus 1 has to be in the null space of this matrix. That's just definition of null space. Right? If it's a full rank, whatever this is, it can only be 0, 0, 0, and that cannot be because this last element is non-negative, non-zero. So we know this has to lie in the null space of this. At least it contains one vector in the null space. So we investigate this joint data space, X and Y together. The approximation is the one I make some adjustment to both X and Y. Okay, this is my approximation to the data matrix because I think this contains noise. If I get to remove the noise, there's a perfect linear model, explain their relationships. So now, from this perspective, it becomes a regression, becomes seeking a low rank approximation because the criterion initially is EX, EY. I want to minimize this. And this A tilde is essentially A plus this. So this thing is essentially A minus A tilde, right? So I want to find A tilde. It's approximation to this. I want this as good as possible. But it has to subject to these constraints. One is its adjustment to this. Secondly, this constraint, they have this, there's a linear relationship between the X and Y. It's just rewriting the regression criteria. Without this doesn't say much. There's no constraints. Just says, there's a trivial solution. EX equals 0, EY equals 0. And the objective value is 0, right? Make no adjustment. That's minimum perturbation. With this, though, this is no longer the optimum. This is not, sometimes it's not even valid because there's noise in it. And there's no, AXY, cannot be, it may not be 0. It's no longer valid, okay? So then we talk about this Acker-Young low rank approximation theorem. If I have matrix A, I do the SVD, I have all these singular values, the rank is R. I'm seeking the best rank K. K is less than or equal to R, somewhere here. Rank K approximation in the following sense. The difference between A tilde and A is any matrix with rank less than or equal to K. The best approximation you could have is to knock out, from SK plus 1 and forward, you knock out all these values to be 0, make them 0. It becomes this matrix. And you can synthesize an AK. That's the best rank K approximation to A. See, this rank K is less than K. Let's say I can just do, K is 3. I can knock out something further, you know, so I just take S1, S2, for example, and S3 I set it to be 0. That will have a larger approximation error, right? I'm using an even lower rank to approximate the original matrix. With more rank, I'm allowed to approximate A little more. If you're looking for rank K, you will use every component in the subspace of K. So we just apply this theorem to our regression problem. In this case, A is X and Y, the joint data space. We are looking for rank D approximation. So A is X and Y, and since A, the size of the matrix n times D plus 1, so it has at most D plus 1. We assume SY is full rank for the time being, so S D plus 1 is not 0, it's greater than 0. Okay, so this is just SVD, we haven't done anything. And we know the best rank D approximation is the one that setting the, you know, SD plus 1 equals 0. So, you know, going from the original D plus 1 full expansion in SVD to remove one component, the last component, okay? And that, compare these two, this, I can achieve A tilde like this only with such EX and EY. This has to be minus of this last component I subtracted, right? So this minus this gives me A tilde, okay? And now this lives in the null space of this one, right? We know that W minus 1 lives in the null space. Remember? This must lie in the null space of this. And of this one, in the null space of this. And we know VD plus 1 is perpendicular to any VI, I from 1 to D, right? So this space, so because it belongs to this null space of this one, 1 to D, SI, UI, VI transpose, it must, so VD plus 1 must belong to the span, of VD plus 1, right? Because each eigenvector is orthogonal to each other. If this is the first D eigenvectors, the last one is the null space of the previous D subspace. So then this can be written as a linear combination of this basis. It's orthonormal. So if this one, the last element it has some values. If the last element is not 0, I can just choose alpha to make it minus 1. And I have some values, let's say, A1 all the way to AD plus 1. If AD plus 1 is not 0, I have alpha times AD plus 1 equals minus 1. I can solve alpha as minus 1 over AD plus 1. And then I can find my W equals this minus 1 over AD plus 1. And here I have A1 all the way to AD. I can just derive from the last singular vector. Okay? Here we assume it has a non-zero last element. So since this one is the right singular value of this data matrix, and it corresponds to the singular value SD plus 1, it is an eigenvector of A transpose A, this matrix, with eigenvalues SD plus 1 squared, right? Basically, if any matrix is USV transpose, then M transpose M, it will be VS U transpose USV transpose, and this cancels out and equals VS transpose S V transpose, right? So this any right singular value must be the eigenvector of this matrix. And in this case, the xy transpose xy, you can write it expanded as such. And since this is the eigenvector, it must be this matrix times this. And also here it corresponds to V S1 square all the way SD plus 1 square. So that means, so this is M, oops. So this means M, oops, sorry. This means M transpose M times V equals V times S1 square to SD plus 1 square. This is just the eigenvector definition. The eigenvector must correspond to the eigenvalue of particular this thing. So then W minus 1 has to satisfy this equation. If we look at the first equation, we have X transpose XW minus X transpose Y equals SD plus 1 square times W. You move this right side, you collect the terms with respect to W, and it's this term and this term. So it becomes X transpose X minus SD plus 1 square I. And you move this constant to the right side. And now we have a form of the TLS solution. It's X transpose X minus SD plus 1 square I and inverse, this matrix inverse times X transpose Y. Okay? If the inverse exists, we have such a form. We look at this, looks very familiar, right? In the ridge regression though, it's like this. So how do we understand this? It seems like a negative regularization. We know in ridge regression, we add something to it, add a diagonal to it. When we subtract, we get nervous, because if this has the reason we introduce ridge regression is LS solution, when the data matrix is rank deficient, we may not have a unique solution. By adding a non-negative lambda to the diagonal, it's guaranteed there's inverse. We can always pick a unique solution. But this one is subtracting certain amount. So if the original diagonal has all non-zero elements, by subtracting this, we may have become zero value, and we may not be able to invert the matrix. So how do we understand this? Why would this be better? Okay? So we have a lot more to talk about it. But before we move on, let's figure out, in the derivation, we have made two assumptions. One is that the last element of VD plus 1, the last singular vector, the last element of the last vector is non-zero. Two, we assume that this matrix is invertible. Can we guarantee that? What are the conditions for that? Here, there's a sufficient condition for it. It doesn't mean that when these are not satisfied, definitely there's no solution. It just says we know for sure if this condition is satisfied, the TLS solution exists and you can invert it. Okay, there's a closed form solution to it, and it takes this particular form. So what are the conditions? These two are just notations. Let's assume the joint data space has these as singular values, and X by itself also have singular values. If the joint data space singular value, the last one, less than TD, less than the last singular value of X, then the TLS has a unique solution and takes its form. So we are going to prove this. We need to show two things. One is to show that this actually exists. We should show that the VD plus 1, we can always calculate VD plus 1, no problem. But can we guarantee this last element is A1, AD plus 1, this thing is not zero? Because otherwise we won't be able to find, we won't be able to find this. This requires, because this is alpha VD plus 1, right? It has to be non-zero because this is minus 1. Secondly, we need to show that this is actually invertible. The proof for the existence, we go by proof by contradiction. Suppose there is A which is not all zero, okay? It cannot be. Suppose that the last element is actually zero, okay? And this is not all zero, okay? It's a very general condition. It cannot be, otherwise VD plus 1 will not be a singular vector. Then, according to the definition, being a right singular vector of this matrix, it means this times this A0 has to be, with this eigenvalue and then with this vector itself. And then we expand it as before, it becomes this. And then if you look at this, look at the first equation. X transpose X, A, X transpose Y times 0, that becomes 0, so that vanishes. And this side is SD plus 1 squared times A. This equation basically says A must be an eigenvector of X transpose X with corresponding eigenvalue SD plus 1 squared. Yes? That's just definition of eigenvector, right? If V is eigenvector of M, we have this equation, right? M applied to V, it's just the V scaled by lambda. It's invariant subspace of M as a transformation, right? So this forms that. So this is just fits that definition, and A is eigenvector of X transpose X with eigenvalue SD plus 1 squared. But that will not be possible because our condition says SD plus 1 is less than TD. And TD is the minimum eigenvalue of X transpose X. This can no longer qualify as an eigenvector. The last one, we assume that the last value is TD. You cannot have an even smaller one that violates the condition. Okay? So that means this doesn't hold. This has to be must have a non-zero last element. So this solution must exist if this condition is satisfied. How do we prove that the matrix in the formula is actually invertible? For a matrix with non-zero eigenvalues, the eigenvalues of this is just diagonal matrix, right? This part. X transpose X essentially is the eigenvalues of this minus this. In the eigensolvers, people constantly use this to deflate the eigenvalue. You can just, like onion peeling, if you know it's 1, you can subtract 1 just to remove this, just do this such adjustment. Anyway, so this equals this, and we know the eigenvalues of this. TD is the last one, so everything must be greater than or equal to this, minus SD plus 1. And since TD is greater than SD plus 1, this is greater than 0. So the minimum eigenvalue of this is greater than 0. The matrix is full rank and invertible. completing the proof, okay? Now, let's try to understand this negative regularization. Let's consider x as some signal x0 plus some zero mean IID Gaussian noise, okay? This is some ground truth, no randomness. It's the original, the earlier noiseless data x we are talking about. Now we just add some noise to it. If you calculate the expectation of x transpose x, the covariance matrix, we substitute this x0 plus z representation into it and expand it. The same term, the quadratic term, is just the covariance of the signal, and that, because it's not a random variable, it's just itself. The other term is this z transpose z, because it's IID Gaussian. It's just the amount of noise you have. And the cross term, because z and x0 are independent of each other, so, and x0 is actually constant, it's not a random variable. I can take it out, and take it out, and we know the Gaussian is zero mean, so these will be zero. So essentially, we derive the covariance of the noisy data is essentially the actual covariance matrix of the data plus the covariance of the noise. And because it's ID, noise is diagonal matrix, essentially it's a sigma square I. Okay? So you can think of, the solution have this form, x transpose x minus SD plus 1, 0, I, right? So this is because x itself has noise. X itself is essentially is x0 transpose x0 plus some noise, sigma I. And the TLS is trying to peel off some of the noise from it. That's why it's subtract SD plus with this amount. Why this amount? Only after peel this much, they lie on the perfect line. They become linearly correlated. When I make such adjustment, x plus EX and y plus EY lines up on the linear space. Okay? That's one view that helps us understand why in the TLS you are doing negative regularization. It's because earlier the x is noiseless. In the TLS, x has noise. It's added with the noise variance. We are subtracting that noise variance. We don't actually know how much noise sigma square is. The best thing we can do is find the minimum adjustment so that they line up in a space. So the last component, SD plus 1, is something that removes the noise and make the linear model possible. There's another perspective at this. So this is to say, TLS solutions of this, if we could denoise, we can recover the signal x0 and use it in OLS. Okay? So let's derive EX. We have derived this, right? The covariance of the noisy data is the actual covariance plus some noise. The expectation of this is expectation of this, and z is zero mean, so it's exactly signal x0. And WOLS, we are gonna use the recover the ground truth x0, right? This is the OLS solution format. But if we can substitute this into this. We re-express x0 transpose x0 as EXX minus EZ transpose Z. Okay? The noisy data's covariance subtracted with the noise inverse. times EX. This X0 is actually EXY. This looks like a TLS solution. But this solution, assuming that we use OLS on the denominator X, okay? The difference though, it's expressed, it's not using X transpose X minus SD plus 1I directly. It's not that, it's taking the expectation of that. In reality, we never know the expectation. What we have is the sample, sample average of these values, right? But that gives us a very interesting perspective. If the data is noisy, we can remove some noise from it. If we're able to do that, we just do the OLS is good enough. On the other hand, if the data is clean, we can add some noise to it. Okay? So if we're going to use OLS, but with the noise augmentation, it becomes equivalent to ridge regression. So this is another view at this. Ridge regression, we have this view. This is derived, we assume X is noiseless. OLS has this solution, right? We can, so why we have this lambda? Why do we add this lambda to it? You know? From this derivation, we can understand, ridge regression is equivalent to ordinary least square regression on original data augmented with noise. What do we mean by that? We have original data, you have these points. We are we can engineer some noise. We ourselves gonna create this noise variable with a variance lambda. If initially I have 10 points, let's say I expanded, each point becomes 20 points. Each time I just add a random sample of noise to it, okay? They have the fixed lambda. The yi has no noise. I just add some noise to x, not y, not target value. So I have multiple solutions. So instead of initially I have this xi, yi, I'm going to create multiple versions like that, right? The x shift location, y is fixed, okay? Then I apply OLS to such noise augmented data, x and y, okay? So this will be, I have this x0 plus z, right? x0 is original data. I add some z to it, okay? And then I'm going to apply OLS, right? And then because this z, because z has this lambda, in the end my ex transpose trans x equals ex0 x0 plus lambda I. That's exactly the ridge regression. Ridge regression over the original data. If the original data is x0, y, ridge over this equals OLS on x0 plus noise and y. This noise is this Gaussian with 0 and a lambda I. Right? This is just by math itself. Okay, so, but on the other hand, you think, why do we bother? Why don't we, initially my data is 1 million. Why do I make it 20 million and solve this OLS, right? sometimes it's still helpful in the following sense. Adding the noise removes coincidental correlations and makes learning more reliable. As we learn from bias and variance trade-off, having more training instances reduces model variance. So for those of you who have touched upon deep learning, there's a lot of data augmentation techniques, right? So you can see a lot of things can be understood even from the very fundamental linear regression. Why data augmentation can improve the model prediction. Okay? So OLS, because it's trying to minimize the y and y hat, you can think of once I find the optimal line, this black line is the best OLS solution. All the vertical prediction error, it's the smallest by least square error criterion. You can think of this is a vertical projection of all the points. Why vertical projection? You can understand it from this, but more importantly, this direction is orthogonal to x. TLS though, x and y is completely symmetrical, right? When you are just fitting, y plus ey and x plus, yes, there's no special treatment. Both have noise. I want to find a line in a joint space. The green line is the best TLS solution, and this solution is best in the sense that each is project to this line, right? Each point project orthogonal projection to the joint space xy. And if you add them up, take the length and square them, add them up, the optimal solution has the minimum orthogonal projection error. So sometimes TLS is called orthogonal regression. It's known as orthogonal regression. This is just vertical because you assume x is golden, no noise in it, you don't touch it. Here you assume x is probably also wiggly. You can't trust as much, so I'm going for the linear space approximation. Okay? Any questions? Yes.
So in your derivation of TLS, so why is x plus x, y plus y less e1 plus x plus?
Originally, so the question was why TLS can be considered a low rank approximation to the joint data space, the data matrix. Yes? That was a question. So if I write the joint data space matrix as A, and my approximation is simply this original thing with adjustment of EX and EY to the X and Y respectively. Earlier, we have shown that this is my TLS criterion. I'm going to minimize this. Introducing this approximation explicitly, I'm minimizing approximator and the original A. I want this to be minimum. Subject to these constraints, this is just the adjustment to be made, and this is causing this to lose one rank. Got it? And then we just apply this Ecker-Young low rank approximation theorem, and the rest follows. Yes?
The value of the case, they could have the low case, and then our comparison is more. So if you have added like what's the right value? So that may not be
right. So the question is, in this low rank approximation, how do we choose the K? So far for TLS, we just apply this. We don't have a choice. We are only looking at, our Y is a scalar. It's only one dimension. So we are only looking at the one rank less approximation. But this theorem is useful for other cases. When you have original decomposition like this, you want to find the rank K approximation. This is actually, you can think of when I knock out all these values, what do I assume? I assume the variation in these minor modes, right? Each mode is just the eigenvector of a matrix. I assume those modes correspond to noise. If I zap them out, all I preserve is signal. So how do I know how much noise in it? If it's a prediction problem, what's our tool to figure out the K? Do I hear cross-validation? Yes? Whenever there is a choice to be made about which model, how much noise in it, the acid test is cross-validation. Okay? Otherwise, you can, let's say the problem is only fundamentally 2D. You get a measurement, the rank is 5D. So this last three is probably superfluous. So you knock them out. This is based on prior belief. But otherwise, you have to look at your task. If you capture the intrinsic relationships, it allows you to make more accurate predictions. Okay? Yes?
Why is TLS not making use of the higher variance in X and Y?
So the question is, why are we not using all the other singular?
No, the other kinds of resources that we have explicit, like covariance matrix or variance for our notice priors, but in TLS we don't make use of that variance.
TLS, the solution to that is the SVD of the joint matrix. Earlier we are looking, remember the Y is just taking for a ride. The only thing matters, the structure of the solution is only dependent upon X, the covariance of X, right? But in this case, this is the first time we introduce noise to X. All the previous model doesn't have that. So we are looking at them together, X and Y, and lose this. One is golden, untouchable. Both X and Y equal. We are allowed to adjust both. So we are looking at the SVD of this matrix. And in the end, it's the right singular vector that matters. In a way, it's a great question in the sense that when we look at the usual least square solutions, we are looking at X transpose X, right? So if X transpose is USV transpose, if X is USV transpose, then X transpose X is essentially V transpose S squared V transpose V. So it's also the case that only the right singular vector that matters. The only difference is here, we are applying the SVD over the joint data matrix, right? This is, again, the new thing is here is that earlier we are looking at inverse of that. So the first few dominant modes participate in the solution. In this case, we are going for the low rank approximation. It takes a different view. The solution becomes different. It's the null space solution that matters. That's why we are looking for the noise vector, the mode that corresponds to the noise. And we are going to talk about principal component analysis. And there we will see the connection better. We'll revisit this problem. Essentially, in a punchline is that here in a TLS solution is PCA solution. PCA can be understood as minimizing the reconstruction errors. That's why you're looking for the null space solution. Okay? Okay. See you next time.